Second speaker this morning is Claude le Bris from École de Ponts, and he'll be talking about stochastic homogenization, some recent theoretical and numerical contributions.
Thank you very much. So thanks for being here. Great thanks for the organizer for inviting me, and more specifically for taking the risk to invite me. It would be stupid in front of such an audience to say I know probability theory. I'm not a probabilist. I grew up in calculus of variation, and today I try to do some scientific computing. Okay? So the question is, why am I here? It turns out that I'm interested in some problems in material science. And although material science can very well be treated by deterministic-like techniques, life is unfair, and what makes materials interesting is defects, is a certain distance to an idealized world. Okay? And therefore, I need some basic tools of probability to try to get closer to the actual materials. And what I'm trying to do today is give you some kind of poor man's view, poor man here meaning computational scientist view, on why and how probability can help in designing more adequate numerical approaches. Okay? So I like to start with a picture. So this is a real composite material. So real means it is a photograph. Okay? It's from EADS, which is for the people from the other side of the ocean. It's the company which built Airbus's aircraft. Okay? It's a two-dimensional cut. And what you see is, I'm not claiming this is a steady state that you are seeing. It's just a picture. Okay? What you see are cross-sections of fibers. So you need to imagine that there are fibers coming out of the screen in the perpendicular direction to the screen. And this cross-section is extremely tiny as compared to the size of the wing. Okay? And from what you see, it's obvious that, of course, these are not periodically arranged. Correct. Everybody will agree to say it's not periodic, even if everybody is wrong, because I didn't specify the period. So if the period is the size of the picture, it can be periodic. But it's not. On the other hand, it's a little bit unfair to say that it's a complete mess. Okay? Of course, I can say, okay, I treat this as a random structure. Okay? I put everything I don't know in some randomness assumption. That's a very convenient and comfortable way of thinking, but the price to pay when you are a computational scientist is that the numerical approach is extremely, extremely expensive and maybe even not tractable. Okay? So what I would like to do is try to find a compromise between being general enough to be able to treat such a structure and being not fully general so that I can compute numbers. Okay? That's the way. So the common denominator of many of the works presented is exactly that compromise. Okay? And more broadly, it's to contribute to making numerical random homogenization more practical. So the line of thought we had was to consider these random materials as random perturbations of a periodic material. So by saying so, I don't say much, because I need to refer the perturbation. But at least what I would like to make you grasp is that in some way, my material will be connected with an idealized world where the material used to be. Okay. Is it me who is? I don't need that, and I don't need any recording. So I mean, it's what? What? Oh, new battery. You see, I exhausted one battery in 5 minutes. So okay. So sorry about that. Let me. Yes. So in some way or another, I mean, my material is a perturbation. It's connected to a periodic material. Okay. So because I want to do new things on the modeling, I concentrate on the simplest possible equation. Okay? So I'm not claiming that what I will do now can be extended to parabolic type equation, to Hamilton-Jacobi type equation, etc. I'm just taking the simplest possible case, which is a divergence equation minus divergence of A grad U is F. A is a scalar field, if you wish. Okay, A is coercive. There is no degeneracy issue. Everything is very simple from the PDE viewpoint. Okay, and on top you have, of course, this idealized world where A is a periodic material, and as I said, the cross section of these fibers is extremely tiny as compared to the size of the picture and the size of the material itself. So there is an epsilon somewhere. Something is oscillating. Okay, at a very tiny scale. Okay, so periodic is very fine, but it's not appropriate for my material. So I can jump to stationary, then it's again very fine theoretically, but the point is that I will have a nightmare to compute numbers. Okay, so I would like you to concentrate for a bit on the third line, which is kind of a compromise and which is this new variant we introduced a while ago. I take A, which is my coefficient. Let's look at this from a mathematical analysis viewpoint first. So I have an A, which is a periodic function, and as the argument of A, I take phi minus 1 of x over epsilon and omega. So the minus 1 here means the reciprocal function. Okay? It's not the inverse, it's the reciprocal. And I assume that the grad of phi is a stationary function in some, let's say, traditional sense. So all of a sudden, everyone in this audience understands that the composition of A with phi minus 1 is not a stationary function. Okay? There is no reason for this to be true. Okay? Now it might be a little bit intriguing to understand why we put assumption on grad phi and not phi itself. Okay? So for this, let me go through this briefly. Why does it happen to me and to no one else?
Somebody's pet elephant.
Okay, so
Try moving it down a bit.
moving it down. Don't tell this to a French person. Okay, here is fine. Okay, we'll see. Okay, so I see my material. On the left, you have your idealized material. It is a periodic structure. So I put a lattice because it's better to understand, but there is no discrete structure yet. Okay, it's a continuum structure. It's just for the sake of pedagogy. Okay, so I have something which is periodic on the left. I have a deformation of this, and I have something which is not periodic on the right. Correct? Okay. And every time I want to do something on the right, I use phi minus 1 to get back on the left. Okay? If it was a numerical analysis conference, I would say, for the finite element guys in the room, on the left you have your reference configuration when you compute all your integrals, and on your right you have your current actual mesh. Okay? So that's exactly what I am doing. Okay? And of course, since I don't know exactly what my material is, the map itself is random. Okay? Okay. So usually in the kind of audience I deliver talk to, I spend 5 minutes on this slide, but for you, everyone grasps this in a second. It's just saying, okay, I will put a discrete stochastic setting, so I have a group action which preserves the measure. So everyone knows this, but I'm just defining my notation here. I assume that the group action is ergodic, and maybe a slight specificity is that I am taking a discrete stationarity. So it's f of x plus k, k being zd, so k is an integer. It's f of x plus k, which is f of x tau k of omega. The reason is that somewhere behind the screen, there is a discrete setting because there is a periodic material. Okay? So the period here is 1. If the period was 2, you get a 2k. Okay? Just to understand. And of course, in this particular formalism, the ergodic theorem goes like that. It means that you have first to integrate over the periodic cell of your reference material, which is capital Q here, and then you take the expectation. Okay? It's just the natural thing, given that you are in this discrete stationary setting. Okay, so I take my PDE, and I put assumption on phi. So I'm assuming phi is a diffeomorphism for almost all omega. It's a change of coordinates. Okay? I assume that no catastrophe happens. It means that phi cannot compress infinitely the material and cannot dilate it infinitely as well. Okay? Just otherwise there are pathologies I'm not able to treat. Okay? And I assume, as I said, that grad phi is stationary, and all this, I call this a random stationary diffeomorphism, just a terminology. So why is grad phi stationary? So as I said, I give you a poor man's view. So if you get this slide, you get basically the proof. Okay? So suppose I consider a B. Think of B as being 1 over A being the coefficient of the minus divergence A. Okay? So B is B periodic composed with this phi minus 1. Suppose I want to compute averages of B. This is what I like to call zero dehomogenization. It's the beginning of homogenization. You want to calculate weak limits, in fact. Okay? So if I want to calculate this kind of integral, what I can do is precisely get back in the reference configuration. So I call y is phi minus 1 of x and omega. And I change the coordinates, which means I change the variable in the integrand. That's all what I'm doing. It's elementary, but it works. So I get inside the integral b periodic of y, phi prime of y and omega. Usually it's a modulus or it's a Jacobian. Here everything is simple in 1D, so it's phi prime. Okay? And then I change the bounds, and then I divide by the length of the integral. And of course, because before I had 1 over r, I have a normalization factor, which is exactly what I need to get back on my feet. And if you look at this, well, you see that if you want to calculate the average of b periodic of y times phi prime, well, the good assumption to put is that phi prime of y and omega is phi prime of y plus 1 to minus 1 of omega. And then it marries well with the b periodic of y. The product gives you a stationary discrete function, okay? And you can, by the ergodic theorem, compute the limit of the integral. And that's what you get. You get, in fact, the expectation of b periodic phi prime. And of course, you have this normalization factor, which gives you 1 over the expectation of phi prime. Okay, so it's elementary, but at least it has the advantage to explain why this is phi prime, or grad phi, more generally, the appropriate object to put in this kind of theory, since you are changing the map. Okay? So for the actual random material, we'll do exactly the same. So just in case someone in the room is not completely familiar with periodic homogenization, a 2-slide crash course on that, because I will need this for the next 2 slides. Okay? So if the material was periodic, which means that if my phi was exactly the identity map, okay, I would be trying to homogenize the periodic elliptic equation, and I know for decades that it requires the solution of the cell problem, which is the periodic cell problem, where I get the corrector from, and then I can express, okay, the homogenized matrix, okay, which is the matrix which will enter the homogenized equation as averages over the unit cell of my correctors times the original matrix. Okay? So it's a 2-step procedure. I solve the corrector problem, then I use the corrector to compute the homogenized matrix. Okay? And once I have the homogenized matrix, I have this equivalent equation at the macro scale. And as a computational scientist, I'm very happy because, of course, the miracle is that on this last equation, there is no epsilon, so I can take the mesh as large as I want. Okay, so that's the story of homogenization in the periodic case in 1 minute. Okay, of course, I'm schematic, but it's roughly that. So now I get back to my case. I have a minus divergence, and it's in red, of this complicated random material. So what I claim, and it's in the true is that it converges as epsilon goes to 0 to the solution of this homogenized equation. And now everything is the same except that the formulae are more complicated. That's all it is, okay? Because I have to get back in the original periodic structure, in the reference periodic structure. I have to pass to the limit, I have to get back to the current structure, etc., etc. So it's a little bit of computations, but there is no surprise. The cell problem, which is down here, is a little bit more difficult to articulate, but it's evidently reminiscent of the periodic problem. It is a kind of a strange mix between the periodic problem and the stationary setting, okay? And the homogenized matrix expresses itself as, you see, determinant of expectation -1, so it reminds you of the 0D case I just gave you. It's a normalization factor. It used to be a distance, now of course it's a volume, okay? And you have the expectation of the integral over phi of the unit cell, which is the unit cell, quote unquote, of your actual material. So it's more complicated, but it's quite spontaneous. But still, what you would like to do now is to somehow formalize that your material is a perturbation. So one way to formalize this is to say that your map is in fact close to the identity map. So you insert a small parameter, eta, which is quite different from the epsilon, which gives you the scales of the heterogeneities of your material. And you Taylor expand with respect to eta. So at 0 order, your map is the identity map. And now you will have a first order psi, and you will put assumption on the psi so that everything goes right for your phi, correct? And then you can Taylor expand everything. So what I do on this slide is formal, but all this can be proven, okay? And you can find, of course, the 0 order homogenized matrix, which is the periodic matrix, okay? And then the first order correction to that, okay? Correction in this terminology meaning correction with respect to this small parameter eta, etc., etc. And the good thing is that, of course, by doing so, your random problem has boiled down to some series of periodic-like problems. So if you are interested by computing, what you can do is compute one order after the other. The cost of computing each order is basically comparable to the cost of a periodic computation. And if you are ready to say that you only want to know your homogenized material at a certain order eta, then of course you can provide a result. If you are not satisfied with that, you say eta is too large, I'm too far away from this periodic structure, so there is no option, you need to go to the random problem itself. But if you are ready to negotiate with the size of eta, you have a computational approach to do this in a series of steps. And believe me, the cost is extremely, extremely smaller than the cost of one single random computation, okay? By one single random computation, of course, I have a list of random computation to get the expectation. Okay, so what I phrase here is just that you have this kind of Taylor expansion of anything which appears in your equation, the homogenized tensor, the corrector itself, etc., etc. Everything can be Taylor expanded, and you can prove that the appropriate order of convergence, which is expected, is in fact attained. Okay. But now, in scientific computing, you can basically always Taylor expand, but if the prefactor is 10 to the 40, you are dead. Okay? If my expansion is very large in terms of coefficients, I'm dead. So I have to find some appropriate test cases to prove that indeed it works, and you can indeed reach a good accuracy within a finite amount of computation. That's typically that. Okay? Okay, so let me skip on that and show you one picture. So I hope this shows. So what I do here is typically the following thing. I have circles inside squares. So that's my reference configuration. And now I deform these circles, which means that sometimes I elongate them or I squeeze them or whatever in a random way. So if you look at this, you see, okay, it's not far from being a periodic structure. it's quite evident to see that there is some periodic structure behind, but it's not a periodic structure, it's a random deformation of that, okay? And I don't necessarily take my deformation to be close to identity, or I take close to identity, I try things with computations, okay? That's my model for testing the approach. Okay, so, I mean, for this audience, let me say it this way. You can indeed compute all the terms, and you can prove things like that. So if you can see the tiny character here, that the real random homogenized coefficient, so although it's homogenized, it's still random, because of course computations are finite size. So if you take an infinite large box, it is deterministic. But in practice, at least on this side of the ocean, and not this side of the channel, so okay. So in France, everything is, to put it short, everything needs to be deterministic at some point because you cannot afford a big box, okay? So then you have the zero order term, then you subtract the minus eta of your first order correction, you divide by eta squared, so the theory tells you that this is a big O of 1, and what you want to test is the size of this big O of 1, because if it's 10 to the 20, you are there. So here it's close to 5, and that's a typical outcome of the computation, to say, okay, you can do things. Okay. But you might be not satisfied, for many reasons, but at least for one, you would like your reference material, your actual material, to be further away from your reference configuration. So here is what you can do. Instead of taking eta, which is your small parameter, taking it deterministic, what you can do is consider b eta of x and omega, that's the second line of the slide, and consider that b eta is small. It is a random coefficient, that is the difference with the first line, and it is small in some appropriate norm, okay? I could do this on the deformation, but to keep things simple, I will do this on a more traditional setting, okay? Just to help you understand what I am trying to do. So I forget the deformation, and you look at the red line. So it's exactly the same spirit, although it's not exactly the same algebra, okay? So I have my random coefficient. It is a superposition of a periodic coefficient plus b eta and another periodic coefficient, and b eta is small. And I could take b eta small in LP norms, LP of omega norms, but in fact, I spare you that because it's basically like the deterministic case. But if I want to do something which is far away from the deterministic case, I will take b eta as a Bernoulli random variable. Sorry for the typo. Okay? Which means what?
Different Bernoullis for different locations.
Yes. Yeah. Okay? So, my reference configuration used to be a periodic set where these black circles were all located in the middle of periodic cells. And now, my actual configuration is close to the reference configuration in the following sense. Most of the time, I do not at all perturb the reference configuration, and I only perturb it once in a while. But when I perturb my configuration, I do perturb my configuration. I delete the circle, okay? So don't misunderstand me. I'm not saying there is the degeneracy here. Let's say that the coefficient is 1 when it is white and 2 when it is black. It doesn't go down to 0, okay? I stay away from all these pathologies again, okay? I want to do simple PDE analysis, but with a complicated coefficient. That's my spirit, okay? So you see what I'm doing. And now I would like to compute the homogeneous, so now the size of the circle is epsilon. I insert that into my coefficient, which is scalar, of my divergence-like equation, and I want to do the homogenization. So if I look at this naively from the viewpoint of a random setting, I have to take an enormous box, blah, 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 and I'm dead computationally. Or for the computation I can afford, I am able to find an accuracy which is not satisfactory. So what I do is the following. So I am a bit loose here, but I'm sure you will get what I do. Formally, the law of the material is as follows. It is a Dirac mass at the at the coefficient A, okay, for each single cell, and I have a perturbation in law which is eta delta C minus delta A. It means that sometimes I replace A by C. Okay, that's what I mean. And now I do this on each cell, and I do this independently on each cell. Okay, so formally, the law of my material is the product of the delta masses up here. You see what I'm doing? Okay. And now I Taylor expand this product. Okay? So the zero order term is the periodic configuration. So I have the Dirac mass sitting at my coefficient A on each cell K, number K, for K running from 1 to n. Let's assume that I have numbered my cells from 1 to n. And then how do I get a first order term? I take a perturbation on, oh, there is a typo here. I take a perturbation on one cell, okay, so this Dirac mass should be C, and then I let all the other cells as A, okay? So please switch the A here and the C here, okay? And I subtract to that the periodic material. This is how I get an eta term, okay, or the one term. So, as I said, I come from the calculus of variation, and this kind of computation reminds me a lot of thermodynamic limit problems. Let's change a little bit the settings, but I guess that in this audience, people are familiar with thermodynamic limit problems. So, you have a theory for a finite size material, or for a finite size molecular system, okay? And you want to find a theory for the infinite size material. So what you do is, okay, if the material is periodic, you pass to the limit by taking the model, dividing by the volume. Okay. Now suppose that the material is not periodic, but it's a perturbation of something periodic. If it's a local perturbation, short-range perturbation, you will not see anything in the thermodynamic limit because dividing by the volume will cancel out any local effect. But now suppose the perturbation is long-range in some informal sense, and so by dividing by the volume, you see something. The perturbation is long range, but it's not periodic. So how do you get the perturbation? Well, in fact, you consider the system where you have the perturbation and you subtract a background, which is the exact same system without the perturbation. Okay? And then you let the size of this combination of system go to infinity. And here you don't need to divide by the volume because it's a big O of one term. So in fact, your theory is the superposition of a theory like the first product where you in fact divide by the volume plus a first order correction which comes from a theory of defect, if you wish. Okay? I'm not pretending anything about the physical validity of that, but from a mathematical viewpoint, it's fair to call this a theory of defect because you have your current material, you subtract a Gilliam, a physicist would say, you subtract a perfect material, and you concurrently let this go to infinity. Okay? There is a line here. I have in a thermodynamic limit setting, I have proofs, but in this setting, I have no proof of that. I have no proof that this first order combination is indeed the first order correction to the product of the measures. Okay? Probably it's an exercise for a first year student in probability theory. For me, it's too difficult. Okay? It's too difficult, and maybe I take 1 minute being very selfish, because after all, I can take benefit of being here. And I give you, if you know how to answer the following question, you will help me a lot. Okay? I cannot give you any wage, but okay. You flip a coin. If it is a fair coin, you can compute any expectation. Now suppose you flip a slightly unfair coin. It means that you have tail with probability 1/2 minus eta, the exact same eta, and you have head with probability 1/2 plus eta. And now you want to calculate, Now I exhausted the computer. Okay. Now you want to calculate an average over your series of draws. Sorry. Whoa. Okay, now you want to calculate an average over your series of draws. But of course, is the average, you need to put condition on your average. You need to say that your average doesn't see any finite numbers of draw, like in the thermodynamic limit process. You can change finitely many draws, it will not affect your result in the average. And you need to say that whatever happens very often, you will see it. Okay? That's basically what you are doing. So you take a nonlinear function. If the function is linear, of course, it's trivial. You take a nonlinear function, which is a function of that you want to average over this long series of draws, and this function is not sensitive to any finite number of draws. Okay? And now you assume that your coin is slightly unfair, which means that eta is small. Can you compute the first order correction to the fair coin? That's my question. If you can do this, that's exactly the same problem that you will be solving, except that there is a little bit of PDE theory, but I will take care of that bit. Okay? Okay. So now, as I said, I wouldn't be telling all this to you if it wasn't working. So sorry for the French, but at least it's obvious. So what do? You take a problem which is simple enough so that you can indeed, once and for all, compute the random thing. Okay? You can afford this for once. Okay? And of course, the random thing is the blue. So in the abscissa, you have the number of cells that you are considering for the computation. It is only in the limit of an infinite number of cells that you reach your homogenized coefficient. Okay? So the blue curve is oscillating and it will converge on the far right here to something like 37 dot something. Now, you would like to compute this exact same number more efficiently. So you take your eta, which is small, and you take the zero order term, which is the periodic thing. So of course, the periodic thing is down here, and it has nothing to do with your actual material, because eta is not exactly zero. Correct? Correct. Now you take the first order correction, which is in cost comparable to a periodic problem. Okay, I don't tell you how I solve it, but it's evident. And your first order correction gives you this number, and you get back to the red line. Of course, it's flat because it doesn't depend on the number of cells, because it's a periodic plus eta times periodic. Okay, and you see that, of course, you get a very good approximation very early. If I zoom this in, and if I calculate the difference between the red and the blue, I will have something which is in eta squared. So if you are not satisfied with this eta squared, you have to pay for the full problem. If you are satisfied, you solve two periodic problems and you are done from the very beginning. So you see, that's why I'm saying that this is not proven, but this should be true, because this is very rare that in computational science you see such an agreement when nothing is true. Okay? But of course, this is not one single outcome. I mean, it's very stable with respect to everything. So it's just due to my poor ability to prove these kind of things, but it should be true. Okay. Now, a couple of days ago, you heard Felix Otto talking about stochastic homogenization and the convergence as the size of the cell you are considering for the computation grows. And he was establishing very clever bounds on the rate of decay with respect to the size, etc., etc. So let me look at this exact same problem, but from a different perspective. I explain you this. First of all, I explain you this in 1D. The problem is similar in 2 and 3D. I'm just trying to be pedagogic here. You'll tell me whether I succeed or not. So, no perturbation now, the full random problem. So the random problem, the corrector is minus divergence A of P plus grad W. So in one dimension, this is this ordinary differential equation. And it's subject to this constraint. Remember that I am in a discrete stationary setting. So if you were continuous, maybe you are more familiar to the expectation of grad W is 0, okay? And grad W is stationary. So here it's the expectation of the integral over the cell of this grad, which is 0. And of course, this gives you the homogenized coefficient. So in practice, one way or another, you can use filters. We use filter. You can use this regularization procedure that Gloria and Otto introduced. More or less, you will have at some point to solve the problem on a finite size interval or with some exponential decay or whatever. So let's think of it as a finite size interval. Okay? Okay. And you replace this expectation by, of course, this condition. The explicit solution of your finite size problem will give you an approximation of the homogenized tensor. In 1D, this is an approximation of your homogenized coefficient. So my notation here, this is A star, star meaning it's homogenized. It's subscript R because it depends sensitively on the size of the box you are solving the cell problem on. And as I said, it is only in the limit of R going to the infinity that you get a deterministic number. But while R is still finite, A star R depends on omega. It is a random number. And in 1D, you can express it like that. And of course, there is a statistical bias, because if you take the expectation of this guy, it's not equal to A star, because the -1 of an expectation is not the expectation of a -1. Even someone like me knows this. Okay? So hopefully you will take care of this bias by using better boundary condition. See the talk by Otto and the work by Gloria and Otto. So you will be able to make this approximation more accurate. But there is another thing. Even if you are able to prove that the variance decreases and how much it decreases when R goes to infinity, there is still a prefactor. Okay? There is still a prefactor that in practice can kill you. So what I'm claiming is that you have A star R of omega, which in the limit of large R go to A star. The rate of convergence is basically given by the central limit theorem, okay? And in the central limit theorem, you have a sigma, and if this sigma is very, very bad, from a practical viewpoint, it's still a plague. So question, using standard techniques, can I somehow decrease this sigma? That's my question. So I'm not after the boundary condition, I'm not after the rate of convergence, I am after the prefactor. Okay? So once you get a good method to improve the prefactor, you can combine it with whatever method to improve the rate. Okay? Hopefully it will do a good job. You are people from Monte Carlo theory, so all of you know antithetic variables approach. When you don't know what to do, you do this. This is exactly the setting we are in. So usually I describe what the antithetic variable technique is on the integration of a simple function. Here I will not do this. I know you know this well. So what is the typical application of this technique in my case? Anytime we will generate a random structure in order for us to compute something on our finite size box, we will generate an antithetic structure. So I'm not telling you how. This might not be quite easy, okay? But suppose, I will give you examples. Suppose I am able, instead of taking capital M realization, of taking capital M over 2 realization, and their capital M over 2 spouses, okay? And then I will marry this in an appropriate way to hopefully decrease the variance in the homogenized coefficient. That's what I'm aiming at. In fact, it works. It works, and we can prove it works. In 1D, that is easy. And if we take back the perturbation setting that I told you about in my first part, in fact, we can prove it works in these weakly random settings. We can also prove it works in some real random 2D problems like the random checkerboard and things like that, but we cannot go much further than this because it all of a sudden gets very, very complicated, okay, from the problem. And we tested that in several 2D situations. I will show you. And what is behind the scene is this question. So again, I'm being very selfish. I know there are many references on that, but so far I've not been able to find in the literature any concrete answer to my question. So what is behind is this very simple elliptic type equation. I have a right-hand side, which in fact for a corrector problem is of a divergence type. This might help in the proof. So I have no control, almost no control on that. I have a control on that, and I want to compute this. That's basically the setting. And the question I ask is if I am able to, practically reduce the variance on A by whatever technique it might be, am I able to prove that I reduce the variance of U? Intuitively, it's clear. In practice, it's another story, okay? It's like, basically delete the differential operator. It's like the question, if I reduce the variance on A, do I reduce the variance of 1 over A? That's exactly the same thing, okay? But of course, it's more technical here. So again, it might be very simple for your community, but for me, I don't know. And that's the main reason why I'm not able to do proofs, because I am able to do computation, and computation show that it's worked very well, okay? Okay, so here is a typical thing. I have my Bernoulli material on the left, so now I don't put the circle, it's just color coding to help you understand, okay? So let's say that they are black and pink, and I have these two structures, and I play with them randomly. And instead of generating a list of such structure and calculating, the homogenized coefficient on those, I'm generating half the list of that, and this is the flip of the left, okay? But of course, I'm taking benefit of the fact that this is 1/2, so for 1/3, for instance, P is 1/3, you need to be a little bit more clever in generating the structures so that you keep the same law, okay? I skip the details because, there is nothing very, very brilliant to do. You need to think of it in your office and you will find, okay? And at the end of the day, it works. So again, here, this is the number of nodes. It's not the same unit as before. It's not the number of cells, it's the number of nodes that I use for the computation. But okay, one way or another, it says that going in this direction, the size of the cell on which I do computation increases, okay? That's why I want. And I'm looking for an homogenized coefficient. And every time I compute something, of course, I have an interval of confidence. That's what I'm doing. So the central line is converging to something which is the actual value of the homogenized coefficient, okay? When I am finite here, I always have a bias. And in fact, the actual value lies somewhere in this interval of confidence. And I want to precisely reduce this interval of confidence, and this is the green thing. So you see, it's not spectacular. With antithetic variable, it's never spectacular because you don't do anything much clever, okay? You don't take benefit of the fact you know something on the law. All what you do is you generate something which has the same law. So it's a poor man's view, okay? But it does reduce the variance, and you need to realize that every time I divide by 2 the interval, I divide the workload by 2 to the d, okay? Where d is the dimension, okay? So if I divide by 5, okay, it's something like even in dimension 2 gives you a factor 25, okay? Which is not completely stupid, okay, in terms of workload, okay? And now, of course, this says what? This says, A, it works, B, you can do much better. And what you can do is typically control variate, okay? But then you need to know something on the coefficient, and this is work in progress, and it will work, and it does work much better, but of course, you need to superimpose some additional knowledge of what your material is. Otherwise, you cannot expect reducing the variance in practice. So here you are on the edge, because either you say, I want to be generic enough so that everybody can use my on-the-shelf tool, or you say, okay, I make things specific, and then I tune my numerical approach in order for it to be as efficient as possible in this particular case. But you lose genericity, of course. Okay? Okay. So, there is one bonus. Because we didn't come to this in the first place. Why did we consider this modification of materials by a random map? Why did we consider this fact of, having defects in the periodic structure? Originally, not on the PDE. And for the last 5 minutes, I won't go until 11, don't be concerned. I just would like to guide you. We will fly over 10 slides. Just to show you that, in fact, these ideas are also valid in a kind of a discrete setting. So not with the PDEs, but with actual discrete structure. So you remember I draw a lattice, and I say this is just for pedagogy. So now my lattice is indeed a lattice. So let's look at that. So I look at the material from a microscopic viewpoint. And I take a metal, so it has a crystalline structure. And let's say for a mathematician, this crystalline structure is cubic. Okay? There are plenty crystalline structures, but it's good enough to do the exercise. And in the deformed, literally deformed, in the continuum mechanics sense configuration, it might be the case, it's amplified here, of course, but okay? It might be the case that your reference periodic configuration, your atomic sites, are indeed displaced by the deformation. And the question you ask is the following. On the left, I am able to do the thermodynamic limit process for a periodic material in order for me to derive from a microscopic theory of energy a macroscopic theory of energy. Would I be able to do the same job on the configuration on the right? So now my lattice is not a periodic lattice, it is a deformed configuration of that. Okay? Maybe it has been deformed before, maybe it was just born like this, I don't know, but it's not periodic. And I still would like to do the job. So the two questions are basically something like, what is the most general geometrical property of an infinite set of particles that allows for the definition of energy per unit particle? And in fact, this is related to homogenization theory. This is the second bullet, which goes back to the first part of my talk. Just concentrate 1 second on the first bullet. What is the most general geometric property? I am a little bit unfair here because what I mean by most general is most general, so that I can do computation. Okay? I can always be more general than anyone before. Okay? But I want to spit out numbers in a finite number of iterations. Okay? And reliable numbers. So that's why I call general. Okay? Okay. So it's exactly like saying, from a poor man's view, again, if I look at my material from the microscopic viewpoint, as a pure mathematician, there is no obstacle to consider this sum. As an applied mathematician, I am a little bit concerned about the convergence. Okay? So it's like saying, okay, instead of considering that, I will divide by 10 to the 46, and I will consider that 10 to the 23 is plus infinity, and I will try to find another approach to calculate this exact same number. That's exactly what I'm saying. So I can do this when the capital Xi's are sitting on periodically arranged sites, and what I would like to do is this when they are sitting on somewhere else. Okay? And so, as I said, I fly over the thing, and I just show you this. Suppose you consider a discrete structure, which is the following one, and I will call this a stationary ergodic stochastic lattice. So, my primary object is a lattice. It's little l of omega, and it's a set of points. It took us a while to realize that the objects that we put randomness on are not the points, but the set of points itself. The reason is that from a computational viewpoint, from a practical viewpoint, and from a theoretical viewpoint as well, of course,
your theory must not depend on the way you label people. Okay? And so saying that this guy is doing this or that is not acceptable because there is no this guy. Okay? So we had to put assumption on the lattices, we had to put assumption on the stationarity of the lattices, etc., etc. I fly over this and I just show you this. In fact, you can pass to the thermodynamic limit for this kind of stationary discrete lattices, which are the cousins of the continuum mechanics setting I was considering before. And all what you need is conditions like those. So the location, which used to be of the point x plus k and omega, so now it's phi of x plus k of omega. It's the exact same phi as before, by the way. Okay? It has something to do with phi of x and tau k of omega, but you may also have a global shift of phi of k omega. So your structure can be stationary in many, many respects. Okay? Well, it might be a little bit difficult to grasp right here, but okay, you'll go for the references. I'm flying with it. And this is for the discrete thing. And what you do is, we used to have this. And then, in fact, Pierre-Louis said, okay, let's differentiate formally with respect to x, which is our continuous variable. And if you differentiate this line with respect to that, to x, you get this line. And this is why, even in the discrete setting, in fact, the grad is present. Okay? And the grad is the appropriate notion, because one other way to phrase this is that nothing should depend on where you put the zero. The zero doesn't matter. Okay? Of course, it's evident. Of course, we should have realized that 2 or 3 years before. It took us a long time to realize that the good assumption was in grad phi. And once it was realized, it was only factoring out the effort to put all this in the context of homogenization theory. Okay? So these are the two faces, okay, of the exact same problem. That's why I took the minus divergence A grad, by the way, because there is an energy behind, okay? Discrete, continuum mechanics, and a little bit of computation behind. We have 5 minutes for coffee. Thank you.
Questions?
And answers. Question.
All right, actually, we have 35 minutes for coffee.
Oh, yes.
So.
Okay. Thank you.